Hello, class. Today we are going to do section 2.3 Systems of Linear Equations in Two Variables. Now, our objectives today are to solve systems of linear equations graphically, solve systems of linear equations algebraically with the substitution method, solve systems of linear equations algebraically with the elimination method, model systems of equations to solve problems, and determine if a system of linear equations is inconsistent or dependent. So, let's look at some definitions. A system of linear equations is a collection of linear equations containing the same set of variables. A solution to a system of equations in two variables is an ordered pair that satisfies both equations of the system. So, let's start by solving a system of linear equations. Here we have the system 3x minus 4y equals 21 and 2x plus 5y equals negative 9. Now, we're going to solve this system using the graphing utility. Okay? And in order to do that, we need to solve both equations we have here for y. So here's what we have. We have 3x minus 4y equals 21. So this is the first system of equations. I'm going to solve that first equation here for y itself. Okay, so the first thing that I'm going to do, let me get my pen active. First thing I'm going to do is subtract off this 3x on both sides. This gives me the negative 4y equals 21 minus 3x. Next, I'll divide by negative 4. And when I divide by negative 4, I need to simplify just a bit here. So the negative here, I'm going to use it to cancel out the negative on the 3x, which will add the negative to the 21. Okay, so this will simplify down into y equals 3x minus 21 over 4. Okay, I'm going to let this be my y1. All right. Up next, I need to solve the second equation for y as well. So I have 2x plus 5y equals negative 9. First thing I'm going to do is subtract the 2x over. This gives me 5y minus 9 minus 2x. So 5y equals negative 9 minus 2x. I'm going to then divide by 5 on both sides. It's going to give me y equals negative 9 minus 2x over 5. This is going to be my y2. Okay. Now, I'm going to graph these equations with the window that contains the point of intersection. Okay, so let's try that real quick on our actual calculator. Okay. So I'm going to pull up my calculator here, and I'm going to graph those two equations. I'm going to go y equals, and then I'm going to type my first equation in, which was, what was my first equation? 3x minus 21 over 4. So I've got, to set it up as a fraction, I've got 3x minus 21 divided by 4. And then I have my second equation. That was negative 9 minus 2x. So negative 9. Let's set it up as a fraction first. So set it up as a fraction. Negative 9 minus 2x divided by 5, I believe. Check and make sure I put the right equation in. Sure did. All right, then I'm going to zoom standard and see if it'll grab it for me. So I see it is indeed grabbing it for me. I am going to turn off my stat plot. So second stat plot, because it seems to be interfering here. I don't want it to interfere. And now I can see clearly just my two lines without any other points interfering. I'm going to do second trace or second calc here and run the intersect command. So I'll hit enter on the first curve, enter on the second curve, and then I will try to get close to the guess point and hit enter a third time so that it will guess and find my point of intersection. Here my point of intersection is x equals 3 and y equals negative 3. So the answer to my system of equations is x equals 3 and y equals negative 3. So if I go back to my PowerPoint, you can see they have these same graphs. When they graphed it on their PowerPoint, they had the same intersection point. So the solution, just like it says up here, the solution is 3, negative 3. Now, that's one way to solve it graphically. Let's look at another way that we could solve a system of equations. Could solve by a method called substitution, where one equation is solved for a variable, and that variable is replaced by the equivalent expression in the other equation. All right, so step by step, here's what's going to happen. Step number one, we're going to solve one of the equations for one of the variables in terms of the other variable. Step number two, we're going to substitute the expression from step one into the other equation to give an equation in the one variable. Step three, we're going to solve the linear equation for the variable. And step four, we're going to substitute this solution into the equation from step one or into one of the original equations and solve this equation for the second variable. Then we're going to check the solution in both original equations, or we will check it graphically. Now, let's solve this system by substitution. Okay. Now, when you go to solve by substitution, you're going to have to solve for a variable in one of the two equations. Okay, so either x or y in either the first equation or the second equation. First equation here is 3x plus 4y equals 10. The second equation is 4x minus 2y equals 6. Now, if I'm going to do the substitution method, I'm going to try to solve for a variable that gives me the simplest equation to input into the other equation. So if I go through here, if I wanted to solve for the x here, right here in the first equation, I'd wind up with a 10 divided by 3, which doesn't give me a whole number, which isn't very nice. If I solve for the y in the first equation, I'd wind up with a 10 divided by 4, which still isn't a whole number. And I'd also wind up with a 3 divided by 4, which isn't a whole number. So it wouldn't be a very nice equation to substitute after solving. If I solve for x in the second equation, I'd wind up with a 6 divided by 4, not a whole number. But if I solve for y in the second equation here, I'd wind up with 4 divided by 2 and 6 divided by 2, which are both whole numbers. So it would give me a nice, neat equation. So I, by that justification, am going to solve for the y in the second equation because it will give me the nicest solution to substitute. Okay, so we will solve the second equation for y. So let's do that. We've got 4x minus 2y equals 6. The first thing we're going to do is subtract 4x over to the other side. So you see we have negative 2y equals negative 4x plus 6. We will then divide by negative 2 on both sides. And we will get y equals 2x minus 3. Okay, that's a nice, neat solution to substitute. Now we're going to take that solution here. We're going to substitute it for the y in the first equation. Okay, and then we will solve. So this is what we're doing. We've got 3x plus 4, and then we'll substitute that y in that equation. So we'll substitute the 2x minus 3 in for y in that equation. Now we have an equation that's totally in terms of x. So we have 3x plus 4 times 2x minus 3 equals 10. I'll simplify that out. First thing I got to do is distribute, right? So I will distribute the 4 to the 2x, and I'll distribute the 4 to the negative 3. So I have 3x plus 4 times 2 is 8. 4 times negative 3 is negative 12. Then I can combine my x's. I can combine 3x and 8x into an 11x. And then I can also add over the 12 to the other side so that I'm combining constants here, and I have 10 plus 12 is 22. Then I'm going to divide by 11. I'm going to see that x is 2. Once I have determined that x is 2, now all I have to do is go back into either of the equations above and plug that 2 in to solve for the y. Now, the easiest thing to do is I already have solved one of those equations for y right here. So I could just plug x into the piece that I've already solved for. Okay, so that's what we're going to do. We're going to plug x into this piece right here. We're going to get y equals 2 times 2 minus 3. 2 times 2 is 4. 4 minus 3 is 1. So I should have the solution y equals 1, x equals 2. You can see where I've solved for it on the second page here. Substitute x equals 2 and the y equals 2x minus 3. You get y equals 2 times 2 minus 3, which is 1. So the solution set here is x equals 2, y equals 1, or 2, 1. Simple enough. Now, let's look at the elimination method. So solving a system of two equations and two variables by elimination. We will rewrite one or both of the equations in an equivalent form that allows us to eliminate one of the variables by adding or subtracting the equations. If necessary, we will multiply one or both equations by a non-zero number that will make the coefficients of one of the variables in the equation equal, except perhaps the sign. We will add or subtract the equations to eliminate one of the variables, solve for this variable and the resulting equation, substitute the solution from step 3 into one of the original equations, and solve for the second variable. We will then check the solutions in the remaining original equation, or we will check graphically. So let's use the elimination method to solve this system. 3x plus 4y equals 10, and 4x minus 2y equals 6. Now with the elimination method, what I'm going to do is I'm going to look through here, and I'm going to see which one is the easiest to cancel. Okay, so here, if I'm comparing my x's, it's really hard to make a 3 into a 4, and it's really hard to make a 4 into a 3. If I'm comparing my y's, though, it's not very hard to make a 2 into a 4. Okay, so it would be really easy to make negative 2y into a negative 4y so that these y's will cancel. So essentially what we're going to do is multiply this second equation here by 2 so that my y's cancel and I'm just left with an x. Okay, so 2 times 4x is 8x, 2 times negative 2y is negative 4y, and 2 times 6 is 12. So all I've done is distribute this 2 to both of these terms, and I've gotten this equation here. Now I'm just going to add the two equations together. Okay, and this, okay, we'll back up a step. It might be easier for you to watch me solve rather than just see the answer. 8x plus 3x is 11x. 4y minus 4y is 0. 10 plus 12 is 22. That's where the 11x equals 22 comes from. Then all you have to do is divide by 11, and you will see that x equals 2. Okay, once you find that x equals 2, go to any of the original equations and plug 2 in for x, and you can find your y. Okay, so that's what they're doing here. And this one, they have chosen to substitute it into, I think, into the second equation. Here, what I'm going to do is I'm going to substitute it into the first to show it works either way. So I'm going to do 3 times 2 plus 4y equals 10. This gives me 6 plus 4y equals 10. I'm going to subtract 6 on both sides. I'm going to get 4y equals 4. I'm going to divide by 4 and get that y equals 1. So my solution set here is x equals 2 and y equals 1. What you'll also notice is this is the same exact equation we saw with substitution earlier. So you can choose which one you feel is easier to do. If you like substitution and solving that way algebraically, go for it. If you like the elimination method better, go for that one and use that one. Either way, you should get the same solution set, x equals 2, y equals 1. Okay? Now, let's look at modeling systems of equations. So we're going to solving some real problems sometimes requires us to create 2 or more equations whose simultaneous solution is the solution for the problem. In this example, we'll talk about medication. A nurse has 2 solutions that contain different concentrations of a certain medication. One is a 12% concentration, the other is an 8% concentration. How many cubic centimeters of each should she mix together to obtain a 20 cc of a 9% solution? Now, we have to break this down into the pieces and parts. Okay, we've got one solution with 12, another solution with 8. We want an overall 9% solution. We also know that the first solution plus the second solution needs to give us 20 cc's of the overall solution. Okay, so we have 2 systems that we're basically going to be working with here. We will begin by denoting the amount of the first solution by x and the amount of the second solution by y. The total amount of the solution is the sum of x and y. And like I just said, the sum of the solution should give you that 20 cc's of overall solution. Okay, then we could take it a step further. We know that the overall combined solution needs to be 9% of the 20 cc's. Well, 9% of 20 cc's is 1.8 cc's, okay, which is the mixture that is added by 12% of your first solution denoted by X, and 8% of the second solution denoted by Y. So 12% of the first solution X plus 8% of the second solution Y should add up to give you 1.8. Okay, so now we have two systems of equations. We have X plus Y equals 20, and we have 0.12X plus 0.08Y equals 1.8. Now you could solve the system however you like. You can solve it by substitution. You can solve it by elimination. I'm going to solve it by elimination on this page, and then we'll talk through substitution on the next page. Okay, so if I'm solving this by elimination, I want my X to cancel out here. I'm going to multiply this first equation by negative 0.12. Okay, this is going to change it into negative 0.12X minus 0.12Y equals, now 20 times 0.12, I believe, is negative 2.4. Okay. If I add those two equations together, my x's cancel out. Okay. I'm left with negative 0.04y equals negative 0.6. If I divide by negative 0.04, then I should get that my y here is 15. If my y is 15, what should my x be? Well, I could plug it back in that first equation real quick and tell you that. Should be x plus 15 is 20, which means that x should be 5. So I need 5 cc's of my first solution, 15 cc's of my second. If I go through here, say you wanted to solve it by substitution instead, you could substitute in 20 minus x for y into that 0.12x plus 0.08y equation. Where did they get 20 minus x? Remember, you got the original equation x. You have the original equation x. Oh, what is going on here? Okay, you've got the original equation x plus y. What is going on here? Wow. It is really not liking. Okay. Yep. So your original equation there. You have your original equation. I'm going to write it down here so it'll stop messing up, hopefully. X plus y equals 20. All they've done is subtract x to the other side to get that. So we got y equals 20 minus x. Okay, that's where that comes from. If you plug that into that other equation, you get 0.12x plus 0.08 times 20 minus x equals 1.8. And then you could simply solve that down for your x. Okay, so you get 0.12x plus 1.6 minus 0.08x equals 1.8. And then you basically combine like terms, subtract the 1.6 over, you get 0.04x equals 0.2, divide by 0.04, get x is 5, which means that 20 minus 5 equals 15. 15 has to be your second solution for your y. Okay, so you can solve it either way. You can solve it elimination or substitution. I think elimination was a little easier there personally, but you can solve it for either one. All right, up next, let's look at dependent and inconsistent systems. Okay, so far we've only looked at unique solutions. In a unique solution, you have graphs that are intersecting lines. Basically, they intersect at one point, and that one point that they intersect at is your answer. This would be our answer in this first one. So you have two equations. Those equations give lines that intersect. Intersecting lines give a unique solution. However, there are two other possible things that could happen. You could have a graph that winds up as parallel lines. Parallel lines give an inconsistent system, and an inconsistent system has no solution. Okay, so in the second example, you have no solution. Why? Because the lines never intersect. They never intersect. They never have a common solution, so they have no solution. You could also have the opportunity to have infinite solutions, and that's where the graphs are the exact same line, and the system is called dependent. So same lines give an infinite number of solutions in a dependent system. So if you notice here, typically when you have the same line, the entire equation is just a multiple of the other equation. So if our first equation is 3x minus 2y equals 4, our second equation is 6x minus 4y equals 8. So if I multiplied the first equation by 2, it's the exact same thing. So 3x times 2 is 6x, negative 2y times 2 is negative 4y, 4 times 2 is 8. They're the same exact line, which means they have an infinite number of solutions in common. Okay, so let's see how it will look algebraically. So you use the elimination method to solve each of the systems if possible. Verify the solution graphically. So let's look at A. A says 2x minus 3y equals 4 and 6x minus 9y equals 12. Okay, with the elimination method here, I would multiply this first equation by negative 3. If I did that, I would get negative 6x plus 9y equals negative 12. If I add these two together now, this cancels out and gives me a 0. That cancels out and gives me a 0. And this cancels out and gives me a 0. So I wind up with a situation where I have 0 equals 0. Now 0 equals 0 is a true statement. Okay. If I have a true statement at the end, then I have infinitely many solutions. Okay. So infinitely many solutions when I wind up with a true statement at the end of my elimination method. 0 equals 0. 0 always equals 0. It's a true statement, always will be a true statement. So we have infinitely many solutions in that system. Let's look at B, however. B, and also you could tell that is the same line. That's what the graph over here was showing, that this turns out being the exact same line. With B, we have 2x minus 3y equals 4 and 6x minus 9y equals 36. All right. In B, I'm going to multiply the first equation by negative 3. This is going to give me negative 6x plus 9y equals negative 12. If I add those together, I get 0 plus 0 equals 24. So here I get 0 equals 24. That's a false statement. 0 does not equal 24. Okay. Because 0 does not equal 24, this is an inconsistent system where I have no solution because the equations never intersect. So here I have no solution. All right. That concludes our chapter 2.3. If you have any questions, don't hesitate to reach out by email. Let me know. Please begin preparing for your first test as it is arising rather quickly. If you have any questions, reach out. And if you need any additional help on this particular chapter, just let me know. I will see y'all next lecture.